Okay, hello and welcome. Welcome to the next session of RoboLaunch at Carnegie Mellon University. This is a series of talks, workshops, and competitions that are alumni and scholar-led with the goal of sharing our passion for robotics with others around the world. I'm delighted today to introduce our next scholar that will be welcoming the speakers and those that are facilitating the session today. Jana, I'd like to welcome you to the session to talk a little bit about the series and to do the introduction. Jana?
Okay. Perfect. Hello, everyone. My name is Jana Zeller, and I'm a second-year computer science student at Karlsruhe Institute of Technology in Germany. This summer, as part of the Robotics Summer Institute Summer Scholar Program, I am working on solving dense video understanding tasks much faster. I have approximately 50 of my fellow students with me in the room today, and I will help to facilitate questions in the room. My fellow scholar Anna and I, with our Robotics RoboLaunch colleagues, will be facilitating the questions and answer session at the end of the talk, and will enable scholars joining us live in this room or online to ask questions. And I will hand over to Anna in order to introduce herself as well.
Hi, my name is Anna. I study biomedical engineering at Technische Universität from Mexico, and I would like to welcome everyone joining us through our live stream. We are looking forward to hearing more from our guest speaker today. Thank you.
Without further ado, it's my honor to introduce today's speaker. Dr. Chalvatzaki is an assistant professor and leader of the Intelligent Robotic Systems and Assistance Group at Technische Universität Darmstadt. Dr. Chalvatzaki earned both her diploma in electrical and computer engineering and her PhD from the National Technical University of Athens. Dr. Chalvatzaki's research proposes novel methods for combined planning and learning in order to enable mobile manipulators to solve complex tasks in in-house environments. Thereby, Dr. Chalvatzaki proposes new methods at the intersection of machine learning and classical robotics, taking the research for embodied AI robotics assistance one step further. For her research, Dr. Chalvatzaki has been awarded the renowned Emily Noether Prize Fund of the German Research Foundation. Thank you for speaking at this RoboLaunch session, Dr. Chalvatzaki. We all look forward to your talk.
Thank you very much. Let me share my presentation. And can you all see my screen now? I hope.
Yes.
Okay, great. So thank you very much for inviting me. I'm very, very happy to be able to reach out to so many different people from diverse backgrounds, in particular undergrad students that they want to make their, steps towards this research direction of AI, robotics, machine learning altogether. So I will tell you a bit about myself, and then I will bring the focus to my research, such that we can have some discussion. I will take you through the topics that I have studied throughout my PhD, how I started, topics that I tackled once I joined TU Darmstadt in Germany, and what is the focus of my research now for the next years. As you may understand, I am quite a young professor, as they call it in Germany, so I am establishing my research and my vision, and I will talk about these things. So the topic of my work, it's called The Path Towards Robot Embodied Intelligence. So let me start 1 second. Okay. So let's talk a bit about what do we mean by embodied AI and what is the difference to the classical AI. The artificial intelligence that you may already know is trying to give to systems the ability to solve problems in a way that humans can solve, or even better than humans. So the embodied AI denotes that the body plays an active role in the behavior learning process through the interaction with the environment. And it is the way, the basic way that humans evolved, and actually babies, for example, during the developmental process are acquiring skills. The embodiment hypothesis actually suggests that intelligent behavior may be acquired by the continual and purposeful interaction of an agent with an environment and the induced sensory motor experience. So you interact with the environment over and over again, and you store them in some memory such that you can learn through this memory. Therefore, my research direction concerns the development of algorithms for embodied AI robotic assistants. So systems, AI systems that are embodied through robots that can move around into the world. And we will talk about this kind of robots, what kind of robots this can be. And they can learn from interactions with humans and the environment. But I will give also a broader impact, let's say a broader motivation about why do I care so much about robot assistants, right? Why do we need to have robots that they can move around in our houses and so on? Apart from the fact of having a robot, a bit better robot than the classical vacuum cleaner robot, you can imagine, it will take care of these day-to-day activities, these household tasks that, for example, are pretty boring and we don't want to spend our time doing every day. I think the greater societal impact will come from the involvement of such robots into hospitals as co-workers, collaborators of doctors and nurses, taking care of day-to-day repetitive activities, for example, delivering the food and the medicine to people in hospitals, taking care of the elderly, either in homes or quarantine patients. Therefore, we can imagine that the need of these robots, in particular due to the fact that we have an ever-aging society, the life expectation is rising, therefore we need to take care of these people. I will give you also a brief overview of what is happening in Germany, the European system. I will just mute it so that it doesn't interfere. I just put some of subtitles so that you can see. So this is a documentary of 2001 from Deutsche Welle. That this is one of the biggest channels in Germany, and they made this documentary about the carers of elderly people. These carers are called the ambulance carers. They go to the houses. They spend there 1 or 2 hours. They give some food and some medicine and some basic care to the elderly people, and then they leave. And then these people stay alone. And these people noted that they are feeling neglected by society. And imagine that Germany, that has actually a very, very good social care system, has already a shortfall of about 30,000 care workers. So we can imagine what happens in other countries. And it is actually a very challenging work that currently nurses and caring staff do not want to undertake. So robotics will be very important to enter our houses. And the vision of having robotic assistants is a very old one. This is a video from the 1967 or 68, where the robot that you can see there is the first robotic manipulator that ever, the Unimate, that ever existed in manufacturing. And directly, the roboticists consider that we should put robots into our houses to make our breakfast. And you can see what was the vision back then. And indeed, after that, we had cartoons like Rosie from Jetsons and even Hollywood movies that would depict the robots having human-like bodies, being able to perceive objects and humans around them. They can learn household assisted tasks, and they can adapt to human needs. And the question is, why don't we have such robots yet? Then in the past, we didn't have such good hardware and algorithms, but now things are changing. Now we have better robots with better capabilities, anthropomorphic bodies with increased dexterity. We have the computational power thanks to the faster CPUs and the cluster of GPUs to accelerate our algorithmic processes. We have cheaper, faster, and more accurate sensors. And thanks to the deep learning revolution, we have better algorithms for perception. However, among the many problems that we need to tackle, I believe that now it's time to address some fundamental problems that are also the key components of my research. And to frame it as a research question, let's say, of what I want to study and what my group is studying. The research question is like, how can we enable embodied AI agents like mobile manipulator robots, as the robot that you can see here in the picture, to learn manipulation skills in open spaces, plan assistive tasks, and interact safely with humans in human environments, which means that they are unstructured environments. It means that the things are not always where they should be every day. So how do we achieve this? I identify certain problems that I want to tackle through my research. So the first one has to do with the hesitant human-robot interaction. What happens usually in research, and due to specific capabilities or specific sub-problems that we need to solve, is that actually the human in the end adapts to the robot and not the other way around. In the end of the day, we would like to have a flow between the two agents to adapt to each other. Then we have restricted and non-generalizable manipulation skills. Due to the introduction of learning, we have seen some impressive result in statically installed manipulators. This means that manipulators that are placed on a table and they can do bin picking in some unstructured settings where there is clutter on the table, and basically we don't care how to grasp anything, we just grasp pins and we throw them in a bin. But this cannot generalize to mobile manipulation, where the whole world is basically your workspace. You should be able to grasp everything and interact with everything in your work. And finally, the other problem is the non-adaptive robot behavior, which means that the robots are not able to scale their behaviors to long horizon tasks that are, for example, subsequent pick and places, opening, closing doors, opening, closing drawers, and so on. So my idea is that we have obviously to introduce learning mechanisms such that we can allow AI robotic assistants to overcome their current limits. And my research vision is that we should couple these machine learning processes together with classical robotics, and this is control and planning, in order to finally endow robots with intelligent behavior. So I believe that there is a midway where these two worlds have to meet, such that we can enable robots to break, let's say, the walls of the labs and enter our houses and our complex environments. So I will talk to you a bit about my path for bringing AI embodied intelligence to robotic assistants, starting from several topics, from understanding human behavior to adapting to human needs, how we can accelerate the skill learning of the robots, and how we can execute long horizon tasks. So let me start with the first topic of the human behavior understanding and prediction. This was the major part of my research during my PhD. During my PhD, I was working into a European project, a funded project by European Union, where the goal was to develop this rollator that would assist humans, elderly people with difficulties in walking, into assisting them, supporting them while working, acting proactively, so that they not allow fall incidents and so on. So my goal was, first of all, to understand how its patient or its elderly person would works, and classify its walking into specific pathological classes, such that we can provide respective control and behavior strategies for the mobile robot to adapt to the human. So one of the first developments that I did, it was to use this laser data that scans in a close distance the walking area of the human, such that we can understand specific events that happen through walking that actually are not so easy to identify when you have pathological walking, which varies a lot. And one of my contributions during my PhD was an online system that would track the legs of the human. We would be able to disambiguate the legs of the single person that you are tracking compared to legs of other people that walk around, and would only need few computational resources in order to perform this. And this would, again, mix classical machine learning with filtering methods that it is mostly, let's say, close to classical control, in order to decide what is in real time, what is the gait phase. And this decision about, okay, what is the phase of the walking, would induce some specific dynamics model for the way that we assume that the legs will evolve in time. And this would allow us to track the way the human is working and also to classify the walking performance. Moreover, if we now fuse the information about what is happening on the leg level with the information about what is happening on the upper body, and we use some pose estimation from the camera that tracks the upper body and some center of mass estimation, and then we train a model that can predict the stability of the human, we can get some let's say, alarms about whether or not the gait of the human is close to risk of fall incidents. And we can use this as an alarm into our robotic system. Now, I want to clarify something for those that I assume that you have not worked with cameras. Our cameras are RGBD. This means that they can capture colors and they can also have a depth measurement. But usually our cameras are so bad that in a very close distance or less than 50 or 30 centimeters, they give you black things or they are super noisy. This is why we rely for the low level on laser sensors that are very expensive, but very, very accurate. And on the high level, that is the higher distance with respect to where the camera is placed on the mobile robot to capture the upper body of the human. And in the end of the day, you need this multimodal understanding of what is happening in the human. Now, I would argue that being able to predict how the motion of the human evolves is fundamental for doing the decision-making to robot assistance when you want to solve problems of human-robot interaction or human-robot collaboration. Our decision processes are fast, but they are not as fast as a human. Therefore, being able to predict in longer horizons what the human is supposed to do after some milliseconds and classify also the activity of the human is very important. So one of our contributions was to study how can we model the whole body of the human and use this information, learn the dynamics, and then use recurrent neural networks in order to predict how this will evolve. Now, I will not put many details. I will just give you an information about how we modeled the human. We took the human skeleton, where we assume that there are specific joints in the body and the limbs that connect these joints. We represented it as a directed acyclic graph. And then we use graph neural networks, that it is a specific type of deep learning that operates over graphs. So it can, let's say, keep the structure of the problem and extract information and dynamics from the problem, such that we can learn these dynamics. This could give us very good results compared to some other state-of-the-art methods about predicting some long horizon motion prediction of the human body. But we also coupled this motion prediction algorithm with some module that would also classify what is the expected activity that the human is doing. Like, is he waving? Is the human doing, writing something, and so on. So we coupled this motion prediction with this activity, or if we could call it intention prediction module. And we showed that in the end, if you have better accuracy in your prediction model, you can actually increase your classification of what is the intention of the human. And we coupled this in some social experiments with an hour robot. If you have ever worked with now, you should know this is a small humanoid robot. It is quite slow in the response time. So being able to predict what the human is doing, it's better, because then you can trigger what the robot should do, for example, to wave at the human and so on. However, just sensing the human from a camera and extracting a pose, it's not enough for understanding intentions. Therefore, again, in this concept of the mobile robotic assistant, we try to utilize as much information as we could have from all the sensors that we have on the robot. So our robot had also a microphone array such that it can capture speech from the human. And we have created this multimodal human intention recognition system that would operate even when the human would be sitting and executing some rehabilitation exercises for, helping them increase their performances, or while they are walking and they would like to stop, and they would wave at the robot stop, and they would also say their intention. And we created this multimodal system that will use natural language understanding and also gesture recognition and some pose estimation in order to fuse them and score what is the most likely intention of the human, such that you can trigger respective behaviors from the robot. The behaviors could be, for example, a response from the robot. For example, if you say stop and you do also the gesture and we classify it correctly, then the robot should say, okay, now we will stop. And you incentivize the human that, okay, now the stopping will start, that will be a smooth stopping while walking, or in these cases, for example, that the human is doing some rehabilitation exercises, the robot will be triggered when the scores come out saying this exercise, for example, we have to execute it once more because maybe the score of the performance was not very, very good. So it's not enough to understand what the human is doing. It's also important that our robots adapt to the humans and all these features about the behaviors of the humans that we can extract. So before I go to further details, I will take a brief note here so that I just inform you about what is reinforcement learning and why is it something that you will see a lot coming up into my research. And I would just try to give you some idea of what it is. So reinforcement learning, it's a class of machine learning methods in which the agent learns how to act from experience. We assume that there is an environment that the agent doesn't know how it works. Consider the agent as an infant that explores a new environment. And the agent has to explore the environment, so move in the environment, collect information, and from this information, collect different states by doing specific actions. We can also collect some rewards. So let's say that you are a kid and you want to put a cube inside a shape that has a cube shape, and you actually do it, and I don't know, some light comes out or some music comes out and you are happy. This is rewarding. Now let's assume that you do something else and you somehow hit your hand, then this is kind of a negative reward or else punishment, so you don't want to do it again. So the agent in model-free reinforcement learning, it learns a control policy or a behavior through this interaction with the environment without knowing what are the dynamics. So it doesn't have some kind of physics law about understanding that if I do this, then the effect will be this, the next state that I will see. This is learned implicitly through the policy by the interaction with the environment. This is the model-free reinforcement learning. Now there is also the part of the model-based reinforcement learning that is more coupled into planning. Now planning we do when we always know our goal. If you know that you want to go from a starting position to a goal position, then you can directly plan your trajectory in order to reach it. However, you may not know still how the world works in order to do this. So in model-based reinforcement learning, what we are trying to do is again have an agent that acts on the environment with some specific mechanism, collects this experience, but uses this experience in order to learn the model of the world, how the world works. For example, consider opening, closing a door. Basically, you know the dynamics of this rotation motion of the door, right? And you can, for example, if there is a hard door, you will adjust your force in order to pull it or to push it and so on. So you have some notion of the physics inside there. So in model-based reinforcement learning, what we are trying to do is actually learn the model and try to plan our actions. And through planning, so the planning, what does it mean? It means that you always consider that if I do this now, and then in the next time step I do this, and then in the next time step, all along till the end of the task, I plan what I am going to do. Like consider I am starting in the morning my day and I do a whole plan of what I want to do. This is planning. And then you can be a bit more safe of what you want to do. While in model-free RL, the agent has to explore without a curriculum of what to do. it just goes around, bumps around, and so on. So it's a bit unsafe. And we will see in a while that model-free RL sometimes is not so good for robotics. And what we are trying to do is match the two worlds together and do model-free decision-making when it makes sense, when you don't know your goals, and do model-based reinforcement learning when you actually want to just learn the dynamics. Keep in mind that learning the dynamics of a very, very high dimensional and complex world, it's very, very, very difficult. So this is why it's actually a very challenging research direction. So in particular, when you are, however, working with humans, you cannot imagine having a robot doing these model-free actions, right? Exploring, imagine the robot going back and forth and stepping over the human. You don't want this. What you want to do is learn the dynamics of the interaction of how the human works and how the robot should best place itself such that whenever it needed, the human will grasp it and we keep the stability. So in this framework, what we created was a model-based reinforcement learning algorithm for human-robot interaction for this coupled navigation scenario, as I call it, where the robot is always in front of the human and the human is in the back walking, and we can sense with the same information that I told you before, how the human is walking, what is the status. We can extract also information about what is the step length of the human and use this information to adapt the robot. So we learn the interaction model of the human, and we can use this model in order to do planning. So the robot can also always try to predict how the human wants to move and how should I adjust my motion. And we act this on the environment, and we always collect new experience by interacting with the human and updating our dynamics till we converge, obviously, to the behavior of this specific human, let's say, user that we show that we perform actually stably in some sense. Now in the results, again, I will not give you so many details. We showed that doing model learning the dynamics, it's actually better than just fabricating equations that could describe the kinematics of this motion. Also because how much can you model the human in the end of the day? You can predict how the human will work, but you cannot exactly learn how this coupled system evolves in time. And we showed better performance in this task. Another way to use reinforcement learning for adapting behaviors of robots is to consider that you have some low-level behaviors, for example, some pointing actions that you have already designed, and that there are certain parameters that are coupled to this. These actions, we usually call them also motion primitives, some primitive actions that we know how to execute them, but maybe there are some parameters that we need to adjust, for example, to make the pointing faster, to change the direction of the pointing, let's say, move the pointing at the head, for example, to look at a person and so on. So in this project during my PhD, I was working with typically development children and also autistic children with autism to create some edutainment mechanisms in order to increase the social abilities of these children. So in this scenario that we designed together with psychologists, it is a joint attention task. The robot doesn't talk to the kid. The kid doesn't know what will happen while being in this room-like environment. Suddenly the robot stands up, starts walking towards the table and starts pointing at a brick that is placed on the table. And here you can see, for example, the brick here. What we want to do is it tries basically to transfer the intention that, oh, I need to grasp this, I cannot reach it, can you please help me, but without saying anything. Exactly like a baby, for example, would say, I want to reach this object there. And we want to see whether or not these children will actually, go there and help the robot to perform this handover. What we used here was a neural network that would take as input the pose of the robot that will sense with external cameras, together with specific features like the gaze direction, the body facing and everything. And then we could output the engagement level to the task. These labels were given to us by the psychologists. So they were in some preliminary experiments with hard-coded controllers We brought some kids, we did these experiments, and the psychologists would mark the ground truth, let's say, labels, and then we would train a neural network to match these estimations. Now, given that we can understand whether or not the child is engaged, we can use this engagement level as a reward signal in a reinforcement learning, a model-free reinforcement learning framework, in which the reinforcement learning algorithm adapts the intensity of the actions. So should I lean forward to point at the object? Should I turn? How many times should I turn to look at the kid such that they can transfer the intention that I want the kid to stand up from his standing position and go and give me the object? And the goal, as in most reinforcement learning algorithms, I forgot to tell you this, is to maximize the expected reward. So the return, the reward that you collect from these interactions. And this is basically the objective that you need to execute. And here our objective was to maximize the engagement of the child. And obviously, when you interact with humans, you should care about safety. Safety is one of the most important challenges right now for bringing robots close into humans. So in our recent work, we proposed a way of extracting the surface of the humans. So in this particular case, again, we have a neural network. We have the training data that we generated from capturing human bodies from cameras and modeling them in simulation, but from real measurements of humans. We would take points around the surface of the human and on the air around, such that we will be able to classify always whether a point it is actually on the surface of the human or not. And this would allow us to reconstruct the surface of the human body. This last one is our solution. And we added a trick, so-called regularization, that would treat the human as a point mass when you are very, very far away, and it would deform to shape the human body when you are coming very, very close to the human. And this is actually quite interesting in different applications of robotics. For example, if you are a drone and you want to navigate in an environment, then you don't care so much for close interaction, so you are caring more about Euclidean distances. But if you are a robot that interacts with a human, like doing handovers and so on, you care about being able to get detailed information about the distances in very close distance to the surface of the human. And we can see here, for example, a real implementation where our robot is approaching the human, and you can see how this distance field, we can actually sample it to be, very far away from the human, and this would be like the protective area of the human, while when we come in close interaction, we want to be closer to the body. We can also use it to do reactive control for the robot, where classical methods would just put some kind of spheres on the body that would represent the collision areas, while in our case, we have a neural network. We can query thousands of points in quarters of milliseconds and get all this information in order to do collision avoidance that would give smoother behavior control of the robot. And obviously, we can use it for human-robot interaction, where here the robot has to follow some waypoint without colliding with the human. Here, the human trajectories were pre-recorded from our lab, and we transferred it into the environment. Of course, you can understand that the human here is not aware of the robot, but the robot is aware of the human. And we can also do reinforcement learning for solving very challenging tasks where, for example, you have to deliver a cup, and you should not overturn the cup. You should not collide with the environment. You should not collide with the human. And apparently, we don't care only for these close interactions. If you have a robot in your home and you want, for example, to set up the table or take off the trash, you want the robot to learn also manipulation skills and be able to operate everywhere. And as I told you, in the common framework of model-free reinforcement learning, where the agent acts on the environment, collects experience, and then trains a reinforcement learning algorithm in order to learn a policy that maximizes this return. requires some millions of interactions. And with real robots, we cannot afford to risk their safety. Therefore, in one of the works, we try to couple model-free and model-based reinforcement learning. So in this case, what we did, we said, okay, let's take these early experiences that the robot is collecting from interacting with the environment and try to imagine how to basically learn the dynamics and imagine how the world actually works and do planning in this approximated environment to imagine what the robot would do. What happens here, I will not go again into many details, is that you imagine this rollout, and because you do planning, you take only the actions that actually make sense, and then you take this information that you basically simulated, and you take the real data, you put them together, and you accelerate the learning. So you imagine transitions without them really happening into the real world. And this allows you to have much better performance. So you see here are some typical reinforcement learning tasks of walkers with difficult dynamics. And you can see with blue the superior performance of our method. And we actually use this algorithm to train a robotic hand. This is a 4-fingered robotic hand, and the task here is to turn a valve till we open it, so till it reaches a desired orientation. And this we trained it from scratch on the real robot. And you can see again how fast and opaque our method is. And what is actually pretty interesting is that the agent actually understood that it only needs 2 fingers to solve this task. So the other 2 fingers of the total 4 fingers, it didn't use it at all. And then we wanted to challenge our robotic hand a bit more. And we have this task that is called in the literature finger gating. The finger gating is a task where, for example, you play with your fingers and you rotate an object inside your hand, and it's like the fingers are gating. So in this case, you have to grasp, rotate, regrasp, rotate, and you break contact with the object. So it's very challenging. You should not drop the apple, and you should rotate the apple till a desired orientation. And you can see again the better performance here. For example, the competitive method that doesn't use planning, it starts to rotate, and in a while, actually, it will rotate a lot. The object, so it doesn't plan. So you can understand that sometimes planning is important. Now, if we wanted to explore better for planning, as you can understand, this is a very, very big problem in robotics. Actually, one of the biggest challenges in robot learning is exploration. How we can do effective exploration to learn the dynamics fast without breaking our robot and without breaking our world or everything around us. And as I told you already before, doing planning, it's very important, especially because you can add additional constraints in the planning process. So you may imagine what I want to do till the end and put some additional objectives. Oh, I don't want the velocity to go too much. I don't want to hit things that I modeled that exist in the environment. So this is very important. However, it's very challenging. And in one of our recent works, we added an additional objective in the planning that I will to tell you very, very briefly what this additional objective means. It incentivizes as an intrinsic reward, as we call it, the agent to go to visit the states in the environment that we didn't visit recently. But still your goal is to maximize this sum of the rewards. So it's an interplay between going to explore while I am planning. So you would say I will deviate a bit to see what is happening a bit outside my plan, but not so far such that you can lose, let's say, track of your goal. So here this robot has a tilted table, and it tries to find the goal. It's not informed that the goal is actually here. It has to stabilize the ball in the tip while going up this tilted table and discover by getting the final reward where the goal location is. And here you can see how the exploration covers the state space such that the robot learns the environment. And we actually used, again, this method to train on a real robot. The first iterations are spent into learning how to balance the ball into this tilted environment. And then later on, when the robot learned this strategy, it actually learned that, okay, I find where my goal is to solve the task. And the last part is the long horizon task execution. And I know that I haven't shown you any mobile manipulators yet, but in our recent work, we actually solved a very challenging problem in mobile manipulation. So as I told you before, mobile manipulation is challenging because the robot has all the world as its workspace. So it can operate anywhere. So one of the main challenges comparing to having a statically installed robotic arm is where should I place my robot such that I can operate in different environments? And this is one of the most challenging actions that we have to do. Now, in robotics, in mobile manipulation in particular, usually you have to take decisions on a continuous action space. For example, where should I place myself? And also on a discrete level. Now, should I operate a grasp or not? Now, in this work, we created an algorithm. What is very important to know is that this algorithm solves this hybrid decision making, but it also takes advantage of prior works in robotics, where they would map the possible poses that the robot, by doing discretization and solving the inverse kinematics of the robot, in order to find whether or not, with a scoring method, whether or not some poses are good or bad. And this is very easy to do. It's basically, it has to do with the way that your robot is structured. Different structures of robot will have some different kind of maps. And therefore, we use this as a data set in order to kickstart our learning process. So we didn't put our robot to do anything in the environment. We collected this data and we did an offline learning to learn already a better policy in the vicinity of the robot. So this is always the local frame where what essentially this map tells you is where should I place my robot base so that I can grasp this 60 pose. So arbitrary poses that I should reach with my hands. Where is the area that I should next place myself? So a one step only operation. And you can see here with high blue is the area with a high probability, and then the red is the lower probability, and see the difference of having a continuous function approximation over this space of placements compared to some discretization that loses a lot of solutions. And it's actually very iterative. You just query and query and query, while here you have a single policy that, given the goal that I want to reach, I will tell you exactly what is the highest probability base placement that you should do. So we created an algorithm that could take this initial information and transfer it to multiple tasks such that you are able, in the end of the day, to augment this policy more and more and more, such that you are able to learn more complex tasks. And the idea behind this algorithm is actually boosting, that it is an old concept in machine learning that tells you that in order to solve a very challenging task, you have to break it down into smaller tasks and always learn the part of the task that it is new. And we outperformed most of the methods that they do reinforcement learning for transferring skills, and also methods for doing mobile manipulation with blue and this color is, I don't know which color it is, brown, let's say it's our methods with a twist in the learning process. And we have transferred this information from just being locally, as I showed you before, to having to navigate from 5 meters away or randomly towards a goal, then to have to reach while avoiding obstacles. And every time we just learn this difference that we didn't know before. We keep all the information and we just transfer. And then we can do grasping when there is a wall, that it is an obstacle. So you just have to go on a particular direction to grasp an object from a table. And also operate grasp where you need to find the clearance when there are other objects in the scene that you don't want to grasp, and again with obstacles. And we transferred this approach directly to our robot without needing any retraining to do random pick and placing on the fly, and you can see a projection of our maps. And not only this, we were able effectively to solve rearrangement tasks where the robot will randomly grasp an object from a randomized scene and take it on the other table and place it in an ordered position. So to do the rearrangement, because in the end of the day, if you learn the base placement and whether you need to execute a grasp or a placement to activate basically your arm and plan a picking or a placing action, it's exactly the same space of operation. So you can effectively resolve these long horizon tasks. And the last work that I am very excited to show you, while it may be a bit challenging to discuss, it's the problem of robotic assembly when you have arbitrary shapes that you need to fulfill. So consider, this is a task that we have, a project that we have with architects at TU Darmstadt in Germany. And the idea there is that an architect designs something in paper or like in 3D. It gives it to you. They tell you, you have these building blocks, find how you're going to build it. This is actually very, very challenging long horizon planning task, depending also on how big is the structure, of how many building blocks they are giving us. And then we have to decide how to place them, how to have a structure that is stable, ensure that the robot can actually reach and grasp objects and place them and so on. So it's a combinatorial optimization problem with very high action spaces. And our idea, again, is to take the structure of the problem, use graph neural networks together with reinforcement learning such that the agent can learn how to execute these tasks. However, it is very, very difficult still to train these networks. So we rely on classical methods of years and years ago in optimization and planning. One of these methods is called mixed integer programming. These problems are actually, when you try to constrain them with many constraints and you have to hand design, all these constraints are actually very difficult to solve. Therefore, we took a very simple version of our problem. We discretized our world and we just solved this optimization where this mixed integer program has to say this object can be placed there, this object can be placed there, but it doesn't have any notion of the physics, because this could make it super challenging for us to model it. And then you will have to resolve it for any different type of design. So what we did is that we took, as we call, a relaxed version of the problem. We collected all the data and we used them to train and guide the GNNRL only on possible solutions that the high level gave us. This only in training. On the low level, we execute classical, again, grasp and motion planning, because as I told you before, if you know your initial position and your goal position, you already have resolved this from the previous level of the reinforcement learning, you can just do planning to execute. And therefore, this medium level, that is the reinforcement learning agent, will understand how to execute actions that do not make these objects collide with each other, or they may not be reachable. And you can see here a heuristic versus our learning method. And we transferred also this directly to the real robot without needing any retraining. And we are very excited to take this methodology actually to the mobile manipulation task right now, to more challenging tasks. So to wrap it up, what we are studying right now is learning methods for intelligent assistants, these embodied AI systems, by developing these hybrid methods that leverage the information and knowledge that we have from robotics together with machine learning for achieving generalization. We want to learn more robust mobile manipulation skills that they can operate in different variant environments. We want to integrate the embodied multimodal perception from the robot, the embodied cameras, the lasers, in order to scan and understand also humans. And we want to keep also the human in the loop by taking into account these safety conditions and plan assistive actions. And finally, we want to interleave planning with learning for solving these long horizon tasks that require, for example, combination of multiple actions. I would like to thank my students and collaborators. And yeah, with that, I finish my talk, and thank you for your patience. I am ready for your questions. I'm sorry if it took a bit longer. I just noticed that I am quite over time.
Thank you so much for taking us into to sharing your vision of where the assistive robotics is taking us. I would like to open with one of the questions asking as to what do you think is the next step behind the behavior prediction algorithms that you mentioned? Could there be any way that they can be emotion reactive and not as much physical as the ones you presented?
I would say that this is a very interesting direction, a very, very nice question. You could imagine that you would need some sort of additional sensors, I would say, so some additional multimodal information. Imagine, for example, if you wear a watch that could somehow takes your heartbeat into account. And then I could imagine that we could couple this information of motion prediction together with emotion, depending, for example, there are works that I can point you also that they rely on the face recognition of certain emotions, that they try to couple it with the body stance, so the poses, because in the case of the kids, when they are excited, they may jump, or when you are sad, you may be front, so your body posture changes. But it's very interesting to be able to predict the dynamics of the evolution somehow if you have some indicators from, I would say, some wearables. This would make it more interesting, but it's a very interesting direction.
Thank you very much. I think we can look at the questions in the room with Jana.
Yes, also a big thank you for your talk from me. Do we have any questions in the room? Yes. Sure, you can come up. The camera crashes sometimes, so we'll see whether that works.
Okay, no problem.
Hello. So yeah, I just had a question going back to the long horizon task execution. So is there any other benefits of being in a continuous space rather than a discretized space, other than like potentially missing solutions?
I mean, you could actually solve it as a discretized problem, but definitely you will lose certain solutions. Now, if we are talking about pose estimation, it makes more sense to actually interpolate in the end of the day on a continuous space. But when we are talking about, and this you could imagine it as a more low-level action, while the decision of whether I should grasp or not, or whether now I should pick or not, because imagine that this operation lasts till the point that the robot comes close to the table in order to grasp something. Now, this decision is discrete because in the end of the day, this is kind of more of a symbolic reasoning. So I would argue that when you want to do continuous control on some level by generating, for example, the next best pose, for example, for your robot, it's better to always keep it on continuous basis, even if it is complicated for various reasons, because we are talking about SE3, which means 3D positions and 3D rotations. I am lucky because on my base, I don't have all this complexity. I only have X, Y position and the orientation, so it's more reduced. But if we were talking about the manipulator, then the space is bigger. However, it's very interesting to study ideas from bridging geometry and differential geometry together with robot learning. And it's quite exciting to see how this brings you. But I would argue that in general, it's better to operate on this lower level in continuous spaces and in the higher level on a symbolic level, so on a discrete space.
Awesome. Okay. Thank you.
Do we have more questions in the room? Yes.
Hi. I was wondering thoughts on future work regarding exploration in sparse reward environments. Do you think that like reward bonuses, like what you did with mutual information, are the way to go, or just your thoughts on that?
Yeah, I really think that entropy in general, so the encoding of the available information, let's say, so that everybody can catch up with us, it's one very interesting way to encode intrinsic motivation. So because in the end of the day, when we are talking about sparse reward, we are talking about environments where the this bonus that you take, that you are doing like a good policy, comes very, very far from your starting point, to give it very abstractly. So I think that, yeah, using entropy and in general information theoretic approaches, it's a very interesting way to encode intrinsic motivation to give these intermediate rewards. Other approaches that are closely related are the empowerment approaches that are also interesting to involve in robotics. But we could also consider that adding entropy on a higher level, or adding the structure of the environment, that as you explore it, you somehow try to keep a structure of the environment, could also give you information on where to explore next. Safety, for example, could also be something that you could consider. I'm always trying to investigate what have I learned, understand what is the safe space, and then try to act and guide the exploration through the safe space. This could be also something that could be coupled in the exploration of for robot learning.
Thank you.
Okay, Anna, I think we can facilitate one more online question.
Yes. How does the framework satisfy safety requirements when the human interacts with the robot in an unpredictable way?
This is exactly one of the reasons why we need to have this coupling of the prediction models together with the safety constraints that we are learning. In essence, what you would need is a probabilistic model over the model of the human, of this prediction model, such that you can capture the uncertainty. So if you are able to, for example, have a Bayesian neural network that can capture also uncertainty over models, or different models that can operate and give you some sort of uncertainty estimation, you could consider using this information in a way to make your robot, for example, more conservative in the way that it will react against the human, or more natural, like following the exact policy that you have when the uncertainty is low. So actually, it's a very interesting research topic, this one, to have uncertainty-aware human-robot interaction. Other question? I can take this question from the chat maybe, or the Q&A that I see.
Yes, sure. Go ahead. Thank you.
So I think, why a close to humanoid robot considering dexterity? How far are we from creating Baymax? Maybe you can elaborate what do you mean with the first one? Like, why is it more dexterous a close to humanoid robot, as I understand, right? Yes, the part of the humanoid-like robot is the fact that it gives you this additional degrees of freedom to operate tasks like manipulation, or even by manual tasks, in a similar fashion that a human would do. Now, why we want it to be like a human, it depends on the application. So if we are talking about robotics that operate socially in social environments, so assistants, nurses, and so on, you would like them to have some sort of, cute kind of face or whatever, to be more friendly with humans, but not go to uncanny valley still. Well, if you are considering a robotic manipulator, mobile manipulator, for example, that operates in manufacturing, actually there what you would see is just a very big base and just an arm on top of it, because you don't care about the interaction. It's just a tool for doing a job. So yeah, dexterity is important, because then you can execute more and more tasks that a human would do, or even better than a human would do it. Now, how far we are from creating Baymax? We are very, very far. In my opinion, we need, not the fluffy kind of safe robot, but as I understand how far we are from bringing these embodied AI agents in the house, I would say that we still need 15 to 20 years into resolving all the problems and the complexity in the real world, from the perception, from the learning, from the planning, from safety, from social cues that we have to take into account, natural language understanding, so many components and so interesting, so many research directions to work on.
Okay, I think we're getting ready to wrap up. Thank you very much for taking us through this interesting journey on assistive robotics and algorithms.
Thank you very much for inviting me. And yeah, if anyone wants to interact more, you can drop me an email whenever you want to discuss something further.
Thank you so much. It was a pleasure.
Thank you. Bye-bye.